Hi, my name is Denzel Carter, and this is Lab 4, Circuits and Capacitors. So the purpose of this lab is to predict behavior of circuits with resistors in series and parallel using multimeters to accurately measure potential and current and be able to use a simulation to test Ohm's law and capacitor charging. So the physics principles used in this lab were Ohm's law, which is V equals IR, charge and energy conservation, capacitor, potential difference, and the loop and node rule. So in this simple series circuit, I connected two batteries to two resistors. And since the resistors are in series, the current is the same everywhere. So I1 equals I2. And from the hand calculations, I found a current to be 0.0204 amps, which is almost identical to the simulation. And when the ammeter is inserted backwards, the same results are found. So when placing a voltmeter in between two different points, 3 volts is found, as that's the difference between the positive and negative side of the wire between the two batteries, adding together their voltage. And the ammeter reads 0 amps because the wire connection has been broken, so current no longer flows. Here are the potential differences in different points around the circuit. And as you can see, if you were to take any point and use the loop rule, you'd get that the 3 potential differences would all add up to 0 from these points. Here's a graph of potential I made. You can see the locations of the circuit below, and the zero slope or flat lines show that there's no potential difference, and the steeper slopes between A and B and E and F are due to the electric fields in these areas being stronger. And as you can see, after F, the potential goes back to 0 and loops back to A. So from the findings that I found, attaching the voltmeter does not alter the current because the current still chooses to move through the wire and not the voltmeter. And placing a parallel ammeter in parallel with the 100 ohm resistor causes the current to go through the ammeter instead of the resistor, and therefore the current increases to 0.06. So the resistances I found from just taking the potential difference findings divided by the current, I found basically to be the same resistances in the wire and ammeter to have 0 ohm resistance. So from the RC circuit, I found that the light bulb, while the capacitor is charging, the light bulb starts bright and dims until off. And in the same manner, when the capacitor is decharging after the battery is removed, the light bulb relights and then dims until off. Extra findings I found: as the capacitor charges, the current in the circuit goes from maximum down to 0 once the capacitor is fully charged, and when the battery is removed, the current goes from its maximum down to 0. So the capacitor charging and discharging times I found between a 10 and 20 ohm bulb are shown below. Here's a graph I made of some information of the time versus the volt versus the ln of delta V divided by delta V initial. And this slope that is found above the chart on the right, through the calculations, was found to be equal to -1 over RC. So then RC is equal to about 5.988 seconds, which agrees from the RC value calculated from just taking 30 ohms of the bulb times the 200 microfarad capacitor, which is 6 seconds. So my final reflection questions: if I had used an actual ammeter instead of an ideal simulated one, a real ammeter has slight resistance, and therefore plugging it in across the wire would add resistance, and therefore the measured current would be slightly lower than the simulation. And if I had used a real battery, real capacitor, and no resistor, in an ideal situation, the capacitor would charge instantly with no resistance being there to stop the flow of charge. But in real life, this would not be the case, as batteries, capacitors, and even wires in real life have small amounts of resistance that make the capacitor charge quickly but not instantly. Thank you.